Remember, for expert live tutoring in organic chemistry, email me at david.jeffrey422@gmail.com. Enjoy the video. In this third video installment of preparing for organic chemistry, we continue with Lewis electron-dot structures, and I teach you how to generate valid and complete Lewis electron-dot structures. So these are the 5 formulas that we're going to develop valid and complete Lewis electron-dot structures for. Let's get started. But before we do, I need to caution you. There is a method for doing this that I want to identify and call out, and frankly I want to discourage you from using. This may very well be the method described in your textbook. This may very well be the method preferred by your professor. But in my experience, that I've been doing this a long time, I feel there's a much better, more intuitive way of generating Lewis electron-dot structures than what you see here. What you see here is a count of all the valence electrons for all the atoms in a formula. And then that count is then divided up by the number of atoms and so on and so forth. And I don't even know the rest of the steps because I reject this as a method that I use to teach my students. And so I can't stop you from using this method if this is something that you're determined to do, but I can tell you that you're going to get much more insight into bonding and the possible bonding arrangements and variabilities in organic chemistry if you don't use this method and do use my method. So what is my method? Well, let's take a look at NF3, right? Nitrogen trifluoride. And so, and what I have here is I do have handwritten sketches, and I do that to save time and also to, frankly, put more realism into what you will soon be doing. So in the first step, I arrange the atoms from the formula. And at the very top, I put nitrogen sort of in the middle or the center, and I surround it by 3 fluorines symmetrically. Now, how did I know to do that? Why do I put nitrogen in the center and say not one of the fluorines? The reason for doing that is because the highest valence atom, if you remember what the definition of valence is, nitrogen is a trivalent element or atom, meaning it generally forms 3 bonds, carbon tetravalent, and the halogen's monovalent. So you wouldn't put a monovalent element, an atom or element that forms 1 bond in the center of a molecule, where it's going to have to form more than 1 bond, right? So that's why we put the highest valence element in the middle and surrounded by the lower valence elements. In the next step, and of course we put the dots in. In the next step, we make the first set of single covalent bonds by circling the individual dots. That's what you see in the middle panel there. And then we convert those circled dots to lines. Those are now single covalent bonds. And we count. And you may either be done at this stage or you may not. Now, we are done at this stage. You can see in the bottom structure that is the complete and valid Lewis electron-dot structure for nitrogen trifluoride. There's an 8 electron count for the nitrogen, central nitrogen, and there is an 8 electron count for each of the fluorines. You can see that in terms of the lone pairs and the bonding pairs. Our next formula is SiH4O4. This is silicic acid, and I do the same. I take the same approach in the top panel. I put the highest valence element, silicon, in the middle, and I surround it symmetrically by 4 oxygens, which are next highest valence, and finally in the periphery, the 4 hydrogens, which are monovalent. I then circle as many pairs of single dots as I can, and I make as many single covalent bonds as I can, and that's done in the second panel. And finally, those circled dots become lines, single covalent bonds. And in the final structure, and I don't show the count, but you can see that silicon has 4 bonds, 8 electrons. Each of the oxygens has 2 bonds and 2 lone pairs for 8 electrons. And of course, the hydrogens only have 1 bond for 2 electrons, the duet rule for hydrogen. This means that we're done, and this is a valid and complete Lewis electron dot structure for SiO4H4 silicic acid. Next up is carbon dioxide. Carbon in the middle at the very top, right, highest valence, followed by the formation of the first set of single bonds in the second panel, leading to the third panel. Now, like I said, you form as many single covalent bonds as you can, and you count. And when we count here, the oxygens only show 7 electrons, right? 3 bonds and 1 dot. And the carbon only shows 6 electrons, 2 bonds, and 2 individual dots. So obviously we're not done. And to complete the octets for these elements, and these are second row elements which must have an octet. These aren't any exceptions, right? So what we do is we then form the second set of covalent bonds, which instead of single bonds are now double bonds. And you can see that in the fourth panel down. And finally, we end up with, we generate the correct Lewis electron dot structure for carbon dioxide, which shows a central carbon atom with 2 double bonds to 2 of the oxygens. HCN, hydrogen cyanide, carbon in the middle, highest valence, hydrogen on the left, nitrogen on the right. We form the first set of covalent bonds and get to the third panel, and we count. Of course, hydrogen is satisfied with 1 bond, but the carbon and the nitrogen are not satisfied. So we form we circle another pair of single dots, right, in the fourth panel, which leads to the fifth panel, and we count again. Carbon now has 7 electrons, and nitrogen has 7 electrons, and therefore we're still not done. And finally, we form a triple bond between the carbon and the nitrogen. We count again, and we can see that Lewis electron dot structure on the bottom satisfies the formula for HCN. Except this also satisfies the formula for HCN, and it satisfies all the requirements for a valid and complete Lewis electron dot structure. So which is correct? What is the structure of hydrogen cyanide? Well, it turns out the structure of hydrogen cyanide is the first structure you saw, and not this structure. Okay? More on that in a moment. Finally, the Lewis electron dot structure for the molecule ozone, O3, right? Central oxygen. We have 3 oxygens in the formula. We put 1 in the middle. We form the first set of single covalent bonds. We count, and the terminal oxygens only have 7 electrons. And then you see in the fourth panel, you see an electron transfer from the central oxygen to one of the terminal oxygens, which generates a plus charge and a minus charge in the fifth panel. In the sixth panel, we see that by doing that, okay, we free up a single dot on the central oxygen, which can then form a double bond with the right-hand terminal oxygen, and we get to the final Lewis electron dot structure for ozone. You can see that's at the bottom. We satisfy the octet rule for all 3 oxygens, but it requires a formal charge on the central oxygen and a negative charge on one of the terminal oxygens. But what about this for the structure of ozone, Lewis electron dot structure for ozone? It satisfies all the rules. It is a cyclic structure. It's the first one you've seen. And there are many, many, many ring structures or cyclic structures in organic chemistry, right? In fact, most important biomolecules, your carbohydrates, your nucleotides in DNA and RNA, these are all cyclic structures. And so this is the smallest ring that can be formed, which is a 3-membered ring, 3 points in space. And it satisfies the formula, O3. It satisfies the octet rule. It turns out this is not the Lewis electron-dot structure for ozone, but there's no way you would know that. What you're looking at in this picture and in the alternative Lewis structure for HCN, you're looking at what we call isomers. And isomers are different molecules with different Lewis electron-dot structures which share the same formula or the same composition. The isomers can be very similar in physical properties and chemistry and reactivity, or they can be entirely different. And there are different classes of isomers. In fact, isomers is one of the 5 essential topics or skills that I'll teach you in this mini course. Remember, for live tutoring in organic chemistry, just email me at david.jeffrey422@gmail.com. I hope you've enjoyed this video.